And we are recording this webinar for you so that we'll post those, and you'll be able to access them at a later date if you like. So with that, I'm going to hopefully share my screen. And the presentation, Dave, can we see this okay?
It looks good, Billy. I see it.
Okay, good, thank you. As I said, we're going to be talking about the new roads and airfields constructed on permafrost. I sent this as a practice, and it's important to recognize that that's exactly what this is. It's a synthesis of what has been done since 1895, and we'll talk a little bit about that. The purpose of the synthesis is to provide designers and construction staff and maintenance with a fundamental understanding of permafrost, to provide them all with the summary of what the practices are and what people have tried. Some of them are maybe controversial. Some of them work in some instances and not very well in others. So we'll be talking a little bit about that as we go through this series of webinars. And again, we'll be talking about some of the successes, limitations, pitfalls, and a couple of problems that we've had over the years.
Yep. That's basically what mine did too. So
someone is not muted. If you mute, please. And it's intended to provide designers with information of where to go, when you need to go, and who you might go to for assistance. So throughout this, we've named other references and given some organizations that you might be able to go to find additional information. It's important that we know what it's not. It's not a detailed manual, and this is by design. Actually, the Alaska DOT and PF decided early on that they didn't want a lot of detail in this. What they wanted was the basic information so that the designer can go to it and get a basic understanding, but also recognize that they need to go to subject matter experts to get additional information. And part of this is also to make sure that when they go talk to them, they know what they're asking and have some idea of the language and the terminology that may be used in all of that. So that's all in here. But as I say, the details, it's not there. In fact, when the first draft of this thing was about twice as long as it is now. And at the behest of the department, we cut a lot of stuff out of there, but I think it makes it a bit more readable as part of that. It's not a set of guidelines. It's important to recognize that. All it's providing you is some ideas and some thoughts and information that you can use to help develop how you're going to go about it, designing on permafrost. But unfortunately, none of us think that we are to the point where we can provide firm guidelines to you. But it does provide some information that will help you make the decisions that you need to be made. And as I've said, it's not a comprehensive body of knowledge. There's a lot more out there. We have tried to gather together a bit of a reference so that you can look at that. And as I said, as well as providing information of who you might go to talk to be able to get additional information. Talk a little bit about the chapter overview. It's divided into 10 chapters. And we've tried really hard to divide it in such a way that it makes it easy for you to go find the information you want. We did not want something that a person had to sit down and read from chapter 1 to chapter 10 in order to get the information. We tried to break it down into bite-sized chunks so that you can go to the part that you want. For example, if you want to know more about just more about permafrost in general, you can go to chapter 3. If if you're looking for geotechnical investigations, you'll go to, or two, sorry, Permafrost is in chapter 2. If you want to know more about geotechnical investigations, then you would probably go to chapter 3 and get that information. You don't have to read all of the chapters in order to get the information you need. However, I think chapters 1 and 2 are important for you to go through before you go through the rest, because after all, we are dealing with permafrost. And chapter 1 is focused on some of the history and a summary of what's contained. So it might be worth reading those. So I would suggest reading chapters 1 and 2, and then looking for the chapters that you need beyond that. So chapter 1, as I said, is a brief history and summary of what's contained in the synthesis. And it also goes over some of the things that is not contained in the synthesis in order so that you know exactly what is and is not here. Misha Konevsky will be talking here in just a little bit about the description of permafrost, how it's formed, why it's formed, much of the common terminology, and a little bit about how to recognize permafrost terrain in all of that. So that's will be here coming up shortly, and I think that's probably it's one of the most important chapters because there seems to be a lot of misconceptions about permafrost, and Misha is probably one of the best I've ever sat down and talked to explaining what it's about, and as far as the applying it to the engineering practice. Then we'll talk Kevin Biela, who works for Corel. We'll be talking in a few moments about geotechnical investigations, what you can and cannot do with geotechnical investigations, and how to use it, and some information of how to determine what techniques you might use when. Again, we're just trying to orient the designer. The real expertise is going to lie in your geotechnical staff, and we certainly encourage you to go to them. But as I say, we want to make sure that as you go through that thought process, that you have the tools to be able to work with the geotechnical folks. Thermal modeling is becoming more and more important to us as time goes along. And we've provided some information on that, giving you some ideas of what you can and cannot do, some of the complexities that may be involved. When might you want to use a one-dimensional or a two-dimensional or even possibly a three-dimensional analysis? All of those things are in there. Doug Gehring will be talking about that in late May. Then we've talked about some of the design alternatives that have been used over the years. There are a number of them. Some came from Alaska, some came from other places, including our colleagues over in Canada. And we talk about those, and we'll talk a little bit about the advantages and disadvantages of those, and of some of those, and when they might or might not work to help you out a little bit. Slope stability in permafrost is a big issue. Bob McCaddy will be talking to us in May about that, some of the techniques that are being used, and even some ideas that he proposes that you may not have seen before, and they're not in common practice at this point, but some ideas of how you might look at that. And then, of course, drainage in permafrost, that's a big issue. It's becoming a greater issue as time goes along. And if you really want to thaw permafrost, the fastest way to do it is add water to the equation. And we're looking at ways that you may be able to mitigate that. And then we also are finding that the roadway embankments themselves are causing issues with damming of sheet flow through the permafrost vegetation, and that's becoming a greater and greater issue for roadways. And we'll talk a little bit about some of the things that the folks in construction need to know. Need to pay attention to, what the intent of the designer was, minimizing disturbance, those kinds of things. We'll be talking about that, and some ideas of what that you might employ should you come up against unanticipated ice. And then chapter 9, best practices in maintenance, to include some of the things of disturbance, drainage, and filling of thermal cracks. Some of those ideas would be presented there. And then finally, and probably one of the least misunderstood or the most understood area, or least understood area in the dealing with permafrost is in the area of climate change. There's a lot of misconceptions out there about climate change and how it's affecting the permafrost and our infrastructure. And we'll be talking a bit about that. And as I say, one of the most important things there is know who to go talk to get the information that you might need. This is one of my favorite quotes, and it's by Chester Purington way back in 1895. A lot of us think about the problems we're having are relatively new, but in 1895, Purington said, "Is a serious detriment to the making of a road in Alaska is the thawing of the ground beneath the moss. It's been a universal experience that whenever the moss is cut into, thawing immediately commences, and the trail, which was passable, becomes a filthy, slimy mass of muds, roots, and broken stone." And I put this up here because I think this is a lesson that it seems that has to be learned over and over and over again as we move forward. I know that in 1944, when they built the Alcan Highway, they had to relearn it. They made the same mistakes again. And then when the Alaska Road Commission came into being, they addressed this issue as well. And I've seen it through my career multiple times that people didn't take the time to heed this warning that Purington gave us. And you know, if I get nothing else across to you today, I think it's important that you learn that whenever you disturb permafrost, you run the risk of massive thawing. And there's lots of photos and pictures and information on that. And so we really need to be paying attention to this statement. Again, as I said, it's a lesson that was relearned in building the Alcan Highway. This is one of the trains of bringing men and material in, and they cut through the permafrost, and we ended up with thawing like this. We think of a lot of the things that we have today as being new and innovative, but as you look back to that, the road design as established by the Road Commission, or the standards they set in 1950, were very much the same as we're looking at today. Avoiding the permafrost whenever possible, locating on south slopes whenever you can. That's something that I know Alaska DOT takes near and dear to their heart, and others. Avoid wet hillsides, slopes or seeping water. It's a dead giveaway that there's likely to be some problems there. Avoid disturbing the moss, as Purington said, and place the material over undisturbed moss carefully. And even location parties are required to walk. I know when I first started with the department back in the 1960s, when we were on permafrost, we did exactly that. Everything was hand cleared, and truly hand cleared. I've got a little different equipment now, but still we want to minimize that damage. And then as the photo shows here, this is actually taken out near Delta. Use of corduroy over soft areas, and Purington proposed that back in the 1890s. And then this is probably one that we don't use anymore just because we've got better equipment, but in cut sections, the Road Commission said use stage construction, the thaw and cut method. I personally would recommend that in today's world. I would recommend that in today's world, but it's because the equipment we got can cut permafrost a lot easier. Okay. A couple of definitions about permafrost. One thing I'll note that engineers tend to describe permafrost as based on the performance when it thaws. So we've got ice-rich, thaw, unstable permafrost, and we have ice-poor, thaw, stable permafrost. So we're really looking at the performance of that permafrost should it thaw. But the scientists tend to look at it more in the direction of how it was formed. Syngenetic permafrost is formed in composition in concert with deposition, where epigenetic is basically like somebody turned the freezer on and started freezing it from the top down. A Yetama syngenetic permafrost is mostly ice. And Misha will be talking about that in a great more difficult detail in that. But in general, it's not absolutely true, but in general, you can think of syngenetic permafrost as ice-rich, thaw unstable, and epigenetic tends to be a little bit more thaw stable, but not necessarily fully thaw stable. But there, by knowing how it's formed, you do get some idea of how it might perform. And Misha, as I say, we'll talk about that a little bit later. Those of you as old as I am probably remember Dr. Ed Rice, and if you get the opportunity to read some of his works, I would recommend them. But he really, you know, when I was taking the Arctic engineering class back in the 1970s, he said there were only 4 basic choices when you're building on permafrost. You can keep it frozen, you can thaw it, you can remove it and replace it, or you can just accept the consequences of thaw beneath the structure. And as often as not, we tend to choose the latter. And I can't fault anyone for doing that, but you really need to take just a little bit of time and figure out which one is best. And we'll be talking about that when we get to the later chapter. And I think chapter 5, it discusses that in more detail. But just be aware that you have a limited number of choices when you are working on permafrost. As far as seeking additional expertise, designers aren't expected to know everything, and you've got a lot on your plate to do, so you're going to be limited or leaning on others for your work. So know your limitations, know what you know and what you don't know, and when you reach those limitations, reach out and help elicit the help of others. Prepare a detailed list of questions that you need answers before sitting down and talking with those folks. And through the synthesis, we provide hopefully enough information that you know what questions you need to ask, and then use those questions to help the subject matter experts formulate their approach to the problem at hand. Understand that the data you get and where to get it, there's a significant cost in collecting that data. So make sure that you collect the data that you need. Think very carefully about that. Work with your subject matter experts to make sure that the data that they're collecting meets your needs. And it's interesting to note that 70 to 80% of all the construction claims revolve around changed conditions, oftentimes like finding ice in some cases. And so using the proper geotechnical investigations and other tools that are available can help avoid that. So construction claims are very expensive. I've seen several of them in the tens of millions of dollars. And really, we would like to avoid that, and many of them can be. Okay, and then make sure that everybody's on the same page. I've seen instances where the construction folks didn't understand what the designer wanted, and perhaps they went out and cleared the right of way when they should not have, or maintenance does some ditching in areas that causes problems, not out of, it was not their intent to do so, but they just didn't understand what the design of the roadway and why why the designer was doing what they were doing. So we need to make sure that the word gets passed down when those concepts are employed. And whenever possible, standardize. It's a good idea that if you standardize your approaches so that it's not different on every project. There are certainly reasons for it to be different on different projects, but where you can start working towards some standardization so that everyone knows what's going on. And that's, right now we don't have that, but it's something that we should strive for. So with that, I've got a couple of minutes for questions, so I'm going to stop sharing my screen in hopes that I can see the chat box.
Billy, the big takeaway on the chat box so far is that the slides were posted before people logged on, so they don't have access to them.
Okay, well, I see that question. I will, while Kevin or Misha is giving his presentations, I will repost those for you. And so that you'll have it, and I'll repost the link to the report.
Great, thank you.
Okay, not seeing a lot of questions at this point, other than people would like to see the slides, and I will take care of that shortly. So with that, I'm going to introduce Misha Kamenetsky, and he wrote the section on the permafrost. And as I say, if you really want to understand permafrost, he's one of the best to sit down and talk to. He's certainly available at the university. I've always found him very willing to talk to anyone that wants to know. So I encourage you, if you have questions, to ask him. So with that, you should be able to share your screen, Misha, and discuss your chapter 2.
Can you see my screen?
Yes, now we can.
Billy, can I start?
I'm sorry, I was muted. Yeah, Misha, go ahead. I can hear you fine. I can see your screen.
Good morning. My name is Misha Kanievsky, and I work for the Institute of Northern Engineering. I came to EF in 2005 as a postdoc, and since that time, I have been working on numerous research projects in various parts of Alaska, including several projects funded by DOT. Most of these projects have been related to field studies of structure and properties of permafrost, various types of ground ice, and permafrost-related hazards. And before coming to Alaska, I was doing very similar permafrost studies in Siberia. The second chapter of the synthesis, as Billy already told us, provides some basic definitions of permafrost-related terms and gives some information on permafrost conditions in Alaska. It's rather small, just 20 pages, including references and figures, and of course it cannot cover all the issues related to the permafrost, even briefly. So we also prepared an extended version of this chapter as a part of another document, a permafrost primer for highway and airport engineers. And in this primer, we present some general information on permafrost, including, again, main terms and definitions. We describe main types of ground ice and permafrost-related hazards, and provide information on distribution, structure, and properties of permafrost in various parts of Alaska. I hope this document will be available too with time. In the multi-language glossary of permafrost terms, permafrost is defined as ground that remains at or below 0 degrees Celsius for at least 2 consecutive years. So it's defined exclusively based on temperature, And that means that it may not necessarily be frozen. For example, saline soils may be unfrozen at temperatures several degrees below zero, but it's still considered to be permafrost. The permafrost occupies large areas in the northern hemisphere, and its thickness at some places may exceed 1 kilometer. The thermal regime of the permafrost is commonly characterized by measuring the mean annual ground temperature at the depths of zero annual amplitude. And usually this depth is not deeper than 15, 20 meters below the surface. In the left figure, there is a famous trumpet curve that shows distribution of ground temperatures with depth and the seasonal variations in the upper permafrost. Ground temperatures depend mainly on the mean annual air temperature, but they also strongly depend on various climatic and environmental factors, including thickness of snow, vegetation, thickness of surface peat, types of soil. So it may be rather complicated, and within the same area, permafrost temperatures may vary a lot. Since 1980s, a significant increase in the permafrost temperatures has been observed within the entire permafrost region, and especially in the areas with cold continuous permafrost, as you can see in the right figure. Permafrost region is commonly divided into 4 permafrost zones based on the percentage of the area underlain by the permafrost. Continuous permafrost zone, where permafrost occupies more than 90% of the entire area, and unfrozen ground may be encountered only under large water bodies. Discontinuous permafrost, 50 to 90%, sporadic, 10 to 50%, and finally, isolated patches of permafrost, less than 10% of the entire area. When we talk about the origin of permafrost, we distinguish the 2 main types, epigenetic and syngenetic. Epigenetic permafrost forms as a result of downward freezing in previously deposited sediment or other earth material. For example, all frozen bedrocks belong to epigenetic permafrost. And generally, when there are no additional sources of water, ice content of epigenetically frozen soil decreases with depth. Syngenetic permafrost is generally ice-rich. It forms as a result of upward freezing during sedimentation that occurs under cold climatic conditions, when the base of the active layer rises following accumulation of a new sediment on the soil surface. And transformation of a part of the active layer into the permafrost occurs in geological terms almost simultaneously with sedimentation. Permafrost commonly contains ground ice when it's hard frozen. And there are several classifications of ground ice. Most of them are rather complicated, and here we try to make it simpler. And we describe 3 major types of ground ice: pore ice, segregated ice, and massive ice. Pore ice fills pores of soils and rocks, and definitely it's the most common type of ground ice. It's in fine-grained soils, it's usually invisible to the naked eye, but sometimes it may be visible in gravels and gravelly sands. Typically, soils that contain only this type of ground ice are so stable, which means that they do not contain any excess ice and will not experience significant soil settlement upon thawing. Segregated ice is formed by the migration of pore water towards the freezing front, where it forms ice lenses and layers, which are usually visible. Lenses and layers form crust structures of frozen soils. I will show you in the second slide, on the next slide. Massive ground ice is a general term which is used to describe large masses of ground ice of any origin, including ice wedges, pingo ice, various types of buried ice, and some other types. To describe frozen soils, we study crust structures, patterns formed by ice lenses and inclusions in the frozen soil. The study of crust structures helps us to distinguish the nature of permafrost. Is it epigenetic or syngenetic? Which is important not only for pure science, but for geotechnical investigations as well. Wedge ice is the most common type of massive ground ice. The ice wedges can be observed in many permafrost regions. Ice wedges form as a result of frost cracking in the wintertime, frost or thermal contraction cracking that occurs in the winter. And then melted water fills open frost cracks in the springtime and forms thin ice veins upon freezing of this water. Cracks and corresponding ice veins are very narrow, not more than 1 or 2 centimeters wide near the surface. But after hundreds of years of this process, really large ice wedges can form. And similarly to the types of permafrost, we distinguish epigenetic and syngenetic ice wedges. Epigenetic wedges grow in previously deposited soils when the ground surface is stable, no new sedimentation, and they can be very wide, but they cannot penetrate really deep because the surface during the entire period of their formation is stable. So it's not more than several meters because the vertical extent is limited by the depth of frost cracking. With syngenetic ice wedges, it's a different story. They form during continuing sedimentation, so they can penetrate through the entire section of syngenetic permafrost. That means that in some areas, the vertical extent can reach almost 50 meters. Frost cracks and corresponding ice wedges create a kind of polygonal nets on the surface. The size of polygons varies from 5 to 40 meters across, and the most common sizes from 10 to 20 meters. Here you can see photos from the Arctic coastal plain of Alaska. There are 2 main types of ice wedge polygons, low-centered and high-centered. Low-centered polygons, they form as a result of very active development of ice wedges when growing wedges push adjacent soils that form elevated rims. Very often inside these polygons we have depressions filled with water. High-centered polygons indicate partial melting of the upper parts of ice wedges. Largest syngenetic ice wedges are typical of Yedema deposits. Yedema is a term for ice and organic rich, syngenetically frozen silty sediments. They can be more than 40 meters thick in some areas. Yedema formed in the late Pleistocene within large areas of Eurasia and North America that were not glaciated at that time during the last ice age. And these deposits accumulated as a result of aeolian, fluvial, and slope sedimentation. Mostly it's wind-blown silt, that's the general idea. But the origin, it can be any other origin too. Ice wedges in Yedema can be up to 10 meters wide, and the vertical extent, as I already told, sometimes may exceed 40 meters. And this is a good example of Yedema, which was exposed in the 35 meters high bank of the Itkilik River. It's a tributary of the Colville River in northern Alaska. This photo shows the central part of the exposure, and you can see really big ice wedges with a rather complicated geometry, which is very typical of Yedema. And sometimes when wedges are parallel to the bluff, you may even see the entire wall formed by almost pure ice. It's another photo of the same site. It's a general view of the exposure from the helicopter. And the length of this exposure was almost 700 meters. But, you may ask me a very reasonable question. Why should we bother? Why should we know the type and origin of permafrost and ground ice? Because theoretically, all we need to know during the geotechnical studies is ground ice content that allows us to estimate potential soil settlement in case of permafrost thawing. Here is just one of possible explanations. If we don't, when we don't have natural or artificial exposures, the only way to study permafrost and to estimate ground ice content is drilling, but the results of drilling can be interpreted in the wrong way. And in this figure, you can see that the massive ice bodies encountered by drilling at different depths can be interpreted either as layers of tabular massive ice or as syngenetic ice wedges. And of course, it's not the same. If we want to estimate the ice content of sediments, we should know the nature and properties of permafrost. And that is why the knowledge of permafrost nature and origin is really important for geotechnical investigations as well. And, talking about investigations, just several words about the drilling methods. The common practice for geotechnical investigations in Alaska is solid stem augering of frozen soil, and usually several split spoon samples are taken from each borehole. Solid stem drilling is rather efficient and relatively fast, but soil description from the auger cuttings cannot be used for appropriate evaluation of structure and properties of the permafrost. And to obtain reliable information, we strongly recommend drilling boreholes using continuous coring methods, at least part of boreholes in some key sites of the study area. Moderately disturbed frozen cores may be obtained by split spoons, hollow stem drilling, or direct push geoprobe drilling. For our studies, we usually use a SIP recorder. It's very convenient and it gives us perfect undisturbed samples, but unfortunately there are some limitations. We cannot drill with the SIP in gravelly soils, and the depth is limited by 6, sometimes 7 meters, and definitely it requires a lot of effort to reach such a depth. When we have a good quality core, we often can figure out what is the origin of massive ice just by looking at this ice. For example, typical wedge ice has very distinctive vertical foliation due to soil particles which were delivered in the frost cracks with snow melt water. Also, this ice contains lots of air bubbles, as you can see in these photos. Very often such ice has dark color, gray, brown, yellow, again due to these soil particles. Epigenetic wedges are rather short, but if we see in our boreholes more than 5 meters of wedge ice, that already means that more likely these ice wedges are syngenetic. In this chapter, we also discuss permafrost-related hazards. Many of them are associated with ground ice aggradation and degradation, and while some of these processes are not limited to permafrost regions and may occur almost everywhere in the areas with cold climate, degradation of ground ice occurs mainly within the areas underlain by the permafrost, and processes of ground ice degradation are the most dangerous, and they may cause significant damage to both environment and infrastructure, including, of course, roads and airfields. Talking about permafrost degradation, we should keep in mind that permafrost thawing itself is not necessarily dangerous. If we have ice-poor bedrock or if we have gravel deposits, it's usually not a big difference if they're frozen or unfrozen. Occurrence of large amounts of ground ice, that's what can create really big problems. And sometimes soil settlement may reach many meters upon thawing of such permafrost. And these are several examples of the ice-rich permafrost in Alaska. It's buried glacier ice, which is rather common in the Brooks Range and the Alaska Range. Ice-rich lacustrine and glacial lacustrine sediments, and of course Yedema, sealed deposits with large ice wedges, which are common in Alaska, and in case of the complete thawing, they can be, and even partial thawing, they can be extremely dangerous for integrity of buildings, roads, and airfields. These are several examples of ground ice degradation. So ice wedge thermokarst, which became really common especially in northern Alaska. You can see degrading ice wedges almost everywhere at the North Slope. Thermal erosion, including both riverbank erosion and formation of thermoerosional gullies, and thermal denudation that results in formation of retrogressive thaw slumps. These processes may be natural, but they also may be triggered by human activities, including road construction. Permafrost in Alaska can be encountered almost everywhere. According to this Permafrost Map of Alaska, about 80% of the state belongs to the permafrost region, including areas with continuous permafrost. It's about 29% of the state. Discontinuous, 35%, sporadic, 8%, and isolated patches of permafrost, also about 8%. This permafrost map also contains some general information on surficial geology, soil texture, permafrost thickness and temperature, very general information on ground ice volume, distribution of pingus and ice wedges, and prevailing thermokarst landforms. Distribution of Yedema in Alaska is especially interesting for us because, as I already showed you, Yedema presents a great challenge to road construction and any other human activities. So Yedema requires a special attention during geotechnical investigations. In Alaska, it has been observed in many areas with mainly continuous and discontinuous permafrost. And within this Yedema region, it is distributed very irregularly. In some areas, it covers only a small percent of territory. And in some other areas, it may be a dominant terrain unit. Main Yedema areas in Alaska include silt belt, In the northern Alaska, it is located along the Arctic foothills, the northern part of the Fjord Peninsula and some adjacent areas. And it's also very common in the interior Alaska. Continuous permafrost exists in northern and northwestern Alaska, including the Arctic coastal plain, Arctic foothills, Brooks Range, and the northern part of the Fjord Peninsula. North of the Brooks Range, permafrost thickness generally varies from 200 to 600 meters in the Prudhoe Bay area, and mean annual ground temperatures vary from about -9 to -4 degrees Celsius. But they also may be close to 0 Celsius, for example, under shallow lakes. And permafrost conditions in northern Alaska are variable. Actually, permafrost conditions are variable almost in any region. But ice-rich deposits with large ice wedges may be observed here almost everywhere. And even without ice wedges, ice content of fine-grained soils is extremely high. For example, the most common crust structure in the coastal region is ataxitic, and the visible ice can, as you can see in this photo, so sometimes it can exceed 70%. The northern part of the Fjord Peninsula is another permafrost region where Yedema is very common. Here we couldn't find any impressive Yedema exposures, just some small ones. But anyway, it's rather easy to recognize Yedema. Actually, everywhere in the continuous permafrost zone with tundra environment. Even if we don't have fresh exposures, there are some clearly visible and recognizable features like salt lake basins, bajorachs, conical thermokarst mounds that form as a result of ice wedge degradation, thermoerosional gullies of very specific shape, and some other features typical of Yedema. It's a different story in the discontinuous permafrost zone. The thickness of permafrost here usually does not exceed 120 meters. And mean annual ground temperatures are much warmer. Commonly they vary from about -3 to 0 degrees Celsius. And very often within this zone, permafrost is absent. Within south-facing slopes, active floodplains in the areas affected by forest fires or development. And permafrost and ground ice conditions in this zone are really diverse. The left figure shows 4 main landscapes, most common across boreal regions of Alaska. Rocky uplands and gravelly sandy lowlands are generally ice poor, and silty uplands are mostly ice rich. In these areas, Yedema is very common, and within peaty silty lowlands, we usually can find layers of frozen peat, superficial peat, several meters thick, underlain by ice rich lacustrine silts, as it's shown in the right figure. It is difficult to distinguish Yedema terrain in the discontinuous permafrost zone because in boreal regions, typical Yedema features are kind of obscured by forests. But we still can see some features. Bajorachs, for example, that indicate Yedema occurrence are sometimes visible mainly in drained salt lake basins, like this one, or old agricultural fields or along abandoned roads. But in most cases, Yedema sites may be detected only by drilling. Based on available information, wedge ice content in Yedema in this region varies from 10 to more than 50% by volume. And the vertical extent of ice wedges may exceed 25 meters, as it was confirmed during our study along the proposed new alignment of the Delton Highway. It's a 9-mile hill area. You can see this profile. The well-known Yedema section has been studied in interior Alaska, has been studied for many decades, since 1960s in the Krell Permafrost Tunnel, which is located not far from Fairbanks. And this is definitely a perfect place to study structure and properties of the syngenetic permafrost. The thickness of permafrost in the areas with sporadic and isolated permafrost usually does not exceed 50 meters. But in some areas, for example, around Bethel, it can be more than 100 meters. And permafrost temperatures here in these southern regions of Alaska are very close to 0 Celsius. And permafrost exists mostly in organic soils or in the areas with very thick superficial peat. But for example, in the very warm Anchorage area, it's still possible to find isolated masses of relic permafrost, and sometimes this permafrost is really ice-rich. For example, during our studies near Birchwood, we described ice-rich silty clay of glacier lacustrine origin, and the soil contained numerous layers of segregated ice, some of them almost 70 centimeters in thickness, and the average volume of visible ice is more than 40%. And considering that the total thickness of permafrost here is close to 10 meters, pretty small, but anyway, we may expect about 4 meters of thaw settlement after complete degradation of the permafrost in this area. And of course, it's unacceptable deformation for any engineered structure which may be constructed on these soils. Yeah, so I think that's all I wanted to show you. Thank you. I don't know if we have time for questions.
Well, okay, thank you, Misha. What we'll do is, Misha, if you could go to the chat box, if there are any questions, go ahead and put those in there. And Misha will answer those questions for you as they come in. We've been answering some of them as they came in for you. So hopefully we got what your questions answered. If not, re-ask it in a different way, and we'll be certainly happy to do that. With that, I'm going to introduce Kevin Biella. And Kevin, if you want to start sharing your screen while I introduce you. Kevin has been working with us for a long time, and he is responsible for the Permafrost Tunnel. And over the years, and I think they just expanded that again yet this year. So it's actually getting larger in size, and the new tunnel is really pretty fascinating. A little bit different than what some of you may have seen in the old tunnels. But anyway, Kevin will be talking to us about use of geophysical methods to characterize permafrost into drilling. It's a rapidly growing field in the area of geophysical investigations. There's also some information in that section about terrain mapping and some of those other kinds of things. But I think Kevin's going to just focus on one part of that today. So Kevin, go ahead and start.
Okay, can you hear me okay?
Yes.
And can you see my slides?
Yes.
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 Okay, great. All right, well, thank you, Billy. And it's going to be pretty hard to follow Misha's footsteps here. He does such a great job with all of the illustrations and his explanations. I'm going to kind of bring it down to more of a wheelbarrow and shovel level. I noticed on the chat there was some interest in drilling. I opted not to talk about the drilling aspect because I kind of thought my audience was all DOTers, but I see the list, it's not. I figured anybody with DOT knows how to drill, and they don't need to be told how to drill. So anyway, I decided to focus on geophysics, and I'll have a few slides here that talk about Permafrost 101, but I won't go too much detail because I know Misha, and I saw Misha went through that. So we'll talk about that. We'll talk about the heterogeneity, which is so important because in the use of the geophysics. Talk about a couple geophysical methods. There's quite a number of them out there, but there's two that we find most applicable to permafrost. And then I'll talk a little bit about application to new design and then application to remediation. And most of this is with a focus on linear or horizontal infrastructure. So I've got a little bit on vertical, but mostly linear. So let's see here. So as we all know, permafrost, the classic definition, anything that's below freezing for 2 or more years, an earth material, I should say. So that doesn't really do much for us really as far as describing exactly what it is. But as we do know, it's either soil or rock with ice. I mean, that's really the ice is the bad actor. If we had just a frozen rock, a below freezing rock, and competent rock, and we took that and put it on our desk and let it sit there for the day, we would probably come back and there would just be a rock sitting there. But if we take frozen gravel or frozen silt or sand and put it on our desk, we'll come back and there'll be a mess all over our desk. It's because of the ice, obviously. So that's what we want to find. And there are some techniques that are pretty good at that. But I like this cross section here because this kind of illustrates what I'm getting at with heterogeneity. And Misha talked about this with the modality of permafrost. We got continuous to the north where it's much colder, summers are shorter. Permafrost is just about everywhere except for maybe under a lake or a river. And then as you move south, as you move towards the equator, you get top-down thawing and you get bottom-up thawing because of the geothermal gradient. So your active layer gets thicker. So your seasonal thawed layer gets thicker. And depending on what's at the surface, maybe there's more forest, less forest, more water, less water, more snow accumulation. Then you start to break up the permafrost, and that's the discontinuous region. In those areas, the permafrost is getting pretty warm. It's generally, around the 28 degrees Fahrenheit, so -3, -4 Celsius on up to freezing. And it's getting weaker because ice is stronger when it's colder. And so as it's getting warmer, not only is it breaking up into blobs and blebs, but it's also getting weaker too. So from a strength perspective, that's something we need to take into account. And then we get down around Anchorage, and there we have very sporadic, as Misha pointed out. But the big thing that I really want everybody to get here is that it's highly variable, both in its extent and its quantity. It can be, I'm pointing to the left, it can be over there, and just 10 feet away, it can be at a much reduced amount, factors less moisture content, just 10 feet away. So that's really important to understand from an engineering perspective. So Misha kind of went over this. Here's an aerial view, or a plan view of Alaska, very continuous to the north, and then grading to sporadic down in the south. And then here's a circumpolar map showing, where Misha resides from in Siberia. Well, there's a good reason why our experts come from Russia. They've got quite a bit of permafrost there, and they've been dealing with it for quite a long time. And then our colleagues from Canada as well. They have a little bit different permafrost. There's a little bit rockier in general, but they certainly have their soil sequences that are ice rich as well. So anyway, that's kind of your circumpolar perspective. But now let's get down to the engineering aspect. Here are some structures that are located on Fort Wainwright. And I picked these just out of convenience. That's where our office is located. That's that upper left photo. These were built in the 40s and 50s. These have full basements, steam heated. If anybody's been in a steam heated building, they know that the basements where the heat distribution systems are, it's like 90 degrees or warmer. These are concrete monsters that generally if there was some settlement, they wouldn't withstand it very well. And not a problem with any of these buildings, yet they were built on frozen gravels. They were built on frozen ground. And all the doors shut, all the windows operate, not a problem with any of these buildings. And then we have pictures like this. Upper left photo, I love this one, a little bookend that's put on the end of this. I think this is in Norilsk maybe, or maybe Misha knows, but a little bit of degradation, permafrost degradation going on around the foundation of this thing. And so they're supporting it. The bottom picture there is a hangar in Greenland where there's about 3 feet of settlement. It's kind of difficult to see, but right where those pallets are sitting, there's about 3 feet of settlement that's occurred in the hangar floor. And then we got roadway degradation off on the right there, center floor spreading, center line spreading on that very right photo. Very classic roadway condition in permafrost. That's actually Goldstream Road leading down to Big El Dorado Creek, and I'll show some more geophysics on that. And then some thawed out caverns up by the University of Alaska. Pretty dramatic, but that's all related to water flow. So what are we dealing with? Well, we've got thaw stable ground. We've got thaw unstable. That's kind of the basic engineering classifications. Thaw stable generally tends to be the coarser grains, and thaw unstable generally tends to be the finer grain soils. I've got some really good pictures here. That upper right, there's two separate samples from the same pit, and then you can see how the thawed condition after baking overnight at 100 degrees Celsius. And then the picture on the left is a full core on the very far left photo there. And then after thawing, you can see that that's about 50% water. And that's taken from the Krell Permafrost Tunnel. And then here's a sample that was just taken off of an auger in Inuvik. You can see the soil sample right after it was drilled, and that was actually kind of loose. So it was very near freezing. Not a really solid sample as it came off the auger flight, but then just 5 minutes later, you see that picture on the right. And then 15, 20 minutes later, the picture at the bottom, super ice rich. That's what we're dealing with. And that has to do with both pore ice, or some people call it matrix ice, the ice that's in between the soil particles, and then intrusive ice. And Misha definitely illustrated that, mostly with what he talked about with wedge ice. And you can see, I can't remember if he talked about the Russian term for what they use called yedema, which I believe translates to ice complex. And you can see that in a lot of his diagrams where he's mapped the upper soil, the upper layers of the strata there. It's just massive amounts of networks of ice wedges. And that's 100% ice. When that thaws, that's an engineering nightmare, let alone the ice-rich matrix ice that's in between. And so we have these illustrations here just to show that, kind of give an illustration. When you have the coarse grain gravels, if they're at saturation, which they generally are when they freeze, there's a little bit of expansion. The soil particles are somewhat pushed apart due to the expansion of the water to ice, but it's not dramatic. And when it thaws, it resettles back. So the settlement, the consolidation is not tremendous. And that's why buildings on Fort Wainwright have seen basically no damage from settlement. But then the finer grain soils, they experience experience extreme segregation, inches to many inches, sometimes feet of segregation ice that gets developed. And when that thaws, that's almost like an ice wedge. It's just pure ice. It ends up being huge displacement. And from an engineering perspective, water has no shear strength. So if you're just thawing an ice wedge, then you're going to have problems with your infrastructure at the surface. And then let's throw on to this climate change. And Vladimir Romanovsky has got some excellent data records going up the Hall Road. And he's got a lot of reports talking about what he's seen. What's interesting is that we don't see a lot of variation in the interior of Alaska, but there's a large warming that's going on in northern Alaska, and this is taking place across the Arctic as well. And I'm not going to go too much into that because that would be a whole discussion in and of itself, and Vladimir and others can do a much better job. But we've got climate change, which is compounding the problem. So let's get into the techniques. The gold standard, everybody does this. This is done for geotechnics around the world. You drill a hole. What better way to get actual information, get your hands on the stuff, and actually take a sample back to the lab and do whatever you need to do for testing, whether it's an expansive clay or a frozen silt. You got to get the stuff to the lab. But typically what we've done is we base our designs off of a drilling program. And without knowing exactly what's in the subsurface, especially with heterogeneous ice content of frozen ground, we do a very systematic drilling. Or if the budget is limited, sometimes it'll end up being a random drilling just to try to maximize the results. But like in the case of DOT, the field manual says for new construction, you drill every 300 feet. How much can you miss every 300 feet? You have to do some mental gymnastics in between. You have to be very experienced. You have to have seen a lot. You have to look at the surface and you have to understand what's going on. Not that it can't be done and not that there aren't very smart people out there that can do that. But for somebody that's learning and for everybody, the general public, it might be a little difficult. So how do we connect the dots in between? Well, sorry, I got this slide here. Misha already, I think actually this comes from Misha. You can see the problem with drilling is how do you interpret? If you really don't know what's going on in the subsurface, if we take that left borehole in figure A and it encounters that layer of ice, it could be, it encounters that section of ice. It could be interpreted as a horizontal lens as it's depicted there, or it could be just the outer edge of an ice wedge. And so you get the picture that the interpretation can be very poor depending on the amount of boreholes you drill. So we use surface geophysics. Hopefully someday we'll have some other methods that are more standoff, like drone or maybe even satellite, but that's a little ways away. But the good thing is that we can connect the dots in a fairly reliable way. The two techniques that I'm going to talk about are electrical resistivity and ground penetrating radar. I'm not going to get into the theory because it's boring, and generally you just don't think too much about that while you're doing it. You just want to know where the ice is. But electrical resistivity is very simple. It's based off of voltage equals current times resistance. And you put a current in and you read a voltage on the other end and you can figure out your resistance. Frozen ground, very ice-rich frozen ground is highly resistive to current flow. Very ice poor or even thawed, especially when it's got water in it, is very conductive. And so that works really well. And you use a triangulation method with electrodes, like what you see in that middle diagram, and you can get to a depth that's applicable for your investigation. The upper right is what we call a pseudo section, and that's what's produced from a resistivity diagram. For all of my diagrams, the red will be very ice rich, while the green and blue will be thawed, maybe even have water content. or I should say very conductive. I actually have an example where that's, well, I'll illustrate that. I won't go into it right yet. And then there's ground penetrating radar. Ground penetrating radar is kind of a default for a lot of folks. They're familiar with it for one reason or another, either maybe having looked for utilities on a project, or I know DOT uses it to look at the very thin overlays of asphalt. You can do that very quickly with a truck mounted radar and just fly down the highway and get pavement thickness and sometimes quality depending on who's reading the radar grams. So it tends to be a method of default, but it's really sometimes it's not very applicable in permafrost terrains. It's really good for infrastructure embankments, and I'll illustrate that. Layered structures is what radar is really good for, horizontally or subhorizontal, and you're reflecting off of that with an electromagnetic pulse, and that's where radar is really good, whereas resistivity doesn't necessarily need that layered structure. So here's resistivity. There's two types. There's galvanic, which is maybe what most folks have seen, where you just pound an electrode, you pound many electrodes into the ground and you connect a cable across those electrodes to a computer and to just a simple car battery. And that's what you see in that upper right photo. That's Pretty Rocks. We did an investigation for Western Federal Lands up there. I think DOT did the drilling on the project. And actually that's been in the news lately. That's a pretty fascinating spot. And then there's capacitively coupled, which actually just gets pulled along the surface. It's a number of receivers. That's what you see in the picture. And then there's a separation via a rope to separate the receivers from the transmitter. And the transmitter is the last one in the line, trailing all the rest of them. There's pros and cons to both. I've got them kind of listed there. You can get very deep with the ERT, but it's a fixed length. You set it up, you have to pound in all the stakes, you have to set it up, it's very manpower intensive, and then you let it run for 4 hours, and then you tear everything down. You can do roll-alongs where you set up the next survey in line, and you then connect, and the computer processing, you can actually get a continuous survey. But you can get very deep, and the resolution is all dependent on how far apart you put those electrodes. Capacitively coupled, you can just drive for miles and miles and miles, keep replacing batteries as batteries go dead, and you can get a really great survey within just a few hours. Really good for road surveys. But its depth is a little bit limited. And, you know, as you can imagine, it's a very long array, and you're trying to drag it on the road. You have to have traffic control, spotters, radios. You got to keep traffic out of your array. If you're in the bushes or the forest, that's a little tough. Things get hung up and you get stopped, and you have to cut line. So there's pros and cons, but overall, the resistivity works really well. And here's a project. This is via Misha. That's why I say it's really hard to follow this guy, because his stuff is so good. And that's why we got him on this project. We wanted to show everybody the applicability of this. And that upper diagram is an ERT survey. All the red, the smeared red, is very ice rich. And then off to the very left, you see very ice poor or thawed, and then very ice poor or thawed to the right. And we drilled every 10 feet, sampled every two feet down through those holes, got moisture content and soil and soil type. And Misha plotted this out, and you can see why the resistivity reads what it does. The area that's very red, that's full of ice wedges, Holocene ice wedges, and very ice rich near the surface, but it starts to get less ice rich down below. The very far left of that is Dead Man Slough. This is out at CCHRC by the University of Alaska Fairbanks. That's Dead Man Slough. That's all thawed out. And so you can see that just shows up on the ERT survey. And then off on the right, we've got very ice poor colluvial sediments coming down from the Geophysical Institute, kind of in that general area of the university. These are very ice poor, and so they show up that way. So very good illustration, excellent illustration, and we validated with extensive drilling. So just a quick little illustration of applicability. This is over by our Farmers Loop site here in Fairbanks. This is the Creamer's Field Wildlife Refuge area. Very open. There's a lot of dog mushing trails and snow machine trails for those that aren't familiar. But we did a transect along one trail, a very straight transect. And if somebody was to ask me to say, put an airfield in this area, say, find the best orientation or the best location, and we'll tell you how to orient it. And if I did my resistivity, this is what I would come up with. That dotted line area, that's Isabella Creek, which is a very shallow running year-round creek, but that area is a very frozen, tussocky, swampy area with a lot of peats at depth. But then as we move to the right by a couple miles, we get into much ice poorer terrain. So just very simply, if somebody was to ask me where would I build an airfield just from the development stage, I would stay away from the left and I would start looking at my planning on the right. And again, we collected this survey in just about 2 hours, processed it in about 1 more hour. And here's the radar. This is the radar system. This is a 200 megahertz system being pulled along the Denali Park Road. We primarily use the monostatic system, which has a receiver and a transmitter both in the same box, but we have used bistatic. They're a little bit more cumbersome, but they do give better results. And we actually use more of the 400 megahertz than we do the 200. The 400 is about the size of a shoebox, maybe a bit bigger. And actually one person can run this. They can have the control at their, they can be pulling along with one hand. In this picture, we opted to have the operator behind while somebody pulled it in the front because it was such a long survey. And here's some of the results from that. This is the Elliott Highway taken before it got reconstructed here a few years ago. And you can see all the individual layers of asphalt that have been put down. And then what we interpret to be massive ice at depth. The one thing about GPR is the signal gets heavily attenuated with water, and it gets heavily attenuated in frozen silts. There's a great paper by Steve Arconi about why frozen silts are so detrimental to ground penetrating radar. But the bottom line is it is a signal robber, and you really won't get too far into frozen ground. So people that say that they see ice wedges with ground penetrating radar, they're not fully informed. You cannot see ice wedges with ground penetrating radar. We have tried. What you can see is the adjoining structures around ice wedges that indicate that they're there. So the indirect indicators of massive ice, you can see those with ground penetrating radar. And they're just really good to see what your infrastructure is doing and where might be some problem areas, and good for water table, good for permafrost table, and good for water table. Here's a couple, one radargram at the Elliott Highway, and you can see where it was specifically identified that that was a patch in those two arrow areas, and you can see the amount of pavement that was pushed down layer after layer after layer, year after year after year. And you know, that's a proven maintenance method, but there it is. You can see it very well with this. Here's another project that I worked on for the Air Force, where we were looking at, they really wanted a building that could withstand heavy floor loads. And so they didn't want to put the structure up on piles. They knew that there was ice-rich permafrost down below, but we were able to investigate with radar, and you can just barely see it in this one radargram. Down at the lower portion there, you see this high reflector. That is a really ice-rich layer that's at the bottom of the glacial sediments, sitting on top of competent bedrock. And that's what's illustrated in that picture on the right. The lower part of that tape measure is competent bedrock. And then the kind of yellowish area there is about, 2 or 3 feet, 2 feet of very ice-rich, decomposed bedrock. Actually, what I showed in that picture way previously where I had baked the sample, that's part of that. And so what we were able to do was we were able to map out that if they dug that out, what would be the volume? And so from an engineering perspective, we were actually able to provide the designers numbers and say, here's how much you would have to excavate out and then subsequently replace with structural fill in order to build a, what I would call a climate neutral foundation. That this is no different than now they can build just like they would build in Florida or California. And the ice is gone. There's no issue for climate change. There's no issue from permafrost. The ice is just gone. The nice thing about this project is we had a ready source of gravel provided by the Greenland ice sheet. And so this was the option that was picked. And so we excavated out over 7 meters of ice-rich glacial material. And now we have a prepared site for perpetuity. Now, from the resistivity standpoint, I want to illustrate this project that was 0 to 8 mile Dalton Highway, where we DOT drilled every 300 feet, but we conducted our CCR survey. And it was very clear, again, the red is high resistivity, the blue and the green is thawed or very ice poor. And you could see that the number of boreholes, and we were able to show that the number of boreholes wasn't really needed. And if we had done this survey ahead of time, we then could have, DOT could have concentrated their boreholes at locations more of interest, like bridge abutments and culvert crossings and things like that. So this is a really good project for a new alignment. This is 9 Mile Hill. Misha already talked about this. We did a number of techniques up there, ground penetrating radar at the top, ERT is the next one down, then Misha's mapping is the third one down, and then CCR is the capacitively coupled is the bottom image. And then here's kind of how it was reproduced. It was reprocessed to provide just a little bit different color schema and then actually isolate out the ice and show the ice very specifically. So you can see the different techniques that can be applied. And then this was another part of 9 Mile Hill where they wanted to know how far they were from the actual top of the permafrost. So we converted our image to show thawed versus frozen. And so red is frozen, thawed is blue. And so that actually provided a depth to permafrost that they could then estimate where to start and stop the insulation that was put up on 9 Mile Hill. And then here's Goldstream leading down into Big El Dorado Creek. This is the borehole drilling, just very simplified with structural fill on top, thawed silts, which would probably indicate that they were once frozen at the beginning of construction way back in 1960 or whenever that road was constructed. I think it was the 1960s. And then we got the frozen silt down below. And then here's radar and resistivity. This is actually starting back almost towards the Velada. Not quite back towards the Velada, but that direction. And you can see the very ice-rich material starting to crop up there on the left of the image. Then we start getting down towards Willow Run area, the Willow Run Road, and we've got some ice. And if those that are familiar with the road right there, there's some very extensive thaw deformation. And then here we're leading down into Big El Dorado Creek. And that long section of very high resistivity, that's that one picture that I showed you with the center line spreading, very ice rich, near surface, very continuous frozen ground that's causing some significant engineering problems. You can see that the radar is helpful, but it's not really providing much. But oftentimes you will see the radar is in conjunction with resistivity. And then here's the runway in Greenland that we use this technique. What was of particular note for us was where the blue is. That turns out that's not water, but that turns out to be a diorite rock. And what we know about our geotechnical investigation is that the diorite rock has a very weathered, ice-rich layer on top of it. So anywhere that we were able to image the diorite with the resistivity, then we knew that's where we had very shallow subsurface ice-rich permafrost, and we needed to protect with insulation. And so I was able to provide the designers with very specific starting points and ending points for the insulation, which was really good, really useful for the contracting process, for bidding and contracting. And then I'll just end us with this slide of the Inuvik to Tuktoyaktuk Highway. Totally different method of constructing. They just push 3 feet of material over the top of unscraped vegetation. And I have yet to drive it since they did this. I hear it's got a lot of issues, which is no surprise. And they knew that that was going to happen. But it's going to be a really interesting experiment in the end what the cost benefit ratio was here. What I often wonder is how they could have benefited from using geophysics from the beginning, run a winter survey from Inuvik to Tuktoyaktuk and see if they could have avoided the really ice-rich areas even better, if that would have helped or not. So with that, I will stop. And if you have any questions, thank you very much.
Okay, thank you, Kevin. As you can see, the synthesis covers a lot of good information, and we're just kind of giving you a little bit of a taste of what's in there. And certainly, if you've got a question, we're not going to be able to stick around too long. But if you got a question, please don't hesitate to drop us a line, and we'll be happy to answer those. But I will say that the geophysical methods, I have driven the Tuck Highway and with some of our Canadian colleagues, and I found that it is fascinating to traverse that terrain. It's significantly different than what we're used to seeing here in Alaska, but they are facing some of the same problems. They are seeing some degradation of the surface. It's going to be interesting to see how that continues to develop over the next few years. It's usually not the first couple of years, but after that you have that. So with that, I'll bring this to a close, and you should be hearing from Dave Waldo here in the not too distant future, establishing a firm date for the next section of this. And we are looking forward to spending a little bit more time with you on that. So Dave, is there anything you want to say before I close it out?
No, just thanks to all the presenters today. And when we get dates, we'll send it out. I imagine that will be in the next week or 10 days.
Great. I thank all of you for attending.
Okay, thanks.